Okay, so welcome to this is the third lecture in this series about quantum channels. In the previous two lectures, we basically went through the derivation of the Lindblad, or the Gorini, Kossakowski, Sudarshan, Lindblad master equation through this functional analysis approach. These next two lectures are going to be more focused on the idea of a quantum channel and different ways of mathematically representing quantum channels and how we work with these representations, okay? So it's going to be a little bit, I would say, more basic. Also, I owe you the proofs of a couple of theorems that we used in the previous lectures, which I will give you here. If you want to read more about these representations, especially more in a modern twist, then my recommendation is this book by John Watrous, which is the theory of quantum information. Actually, kind of the idea of the proofs and the way that I'm going to present it is very much influenced by the way that it's presented in John Watrous's book, okay? So let's start with just to remind ourselves, because I'm going to call them quantum channels because I don't want to say completely linear, completely positive trace-preserving map. So I'm just going to define it once and be done with it. Okay, so this is the definition of a quantum channel. You will often hear it being called a quantum operation or a CPTP map, or it goes by many names, okay, but I'm going to just stick with a quantum channel. And this is that we have a map E. This map will generally take bounded operators from some Hilbert space, which I will call Hilbert space 1, into some other Hilbert space 2. These two Hilbert spaces aren't necessarily the same Hilbert space, okay? So we say that a linear map, a map E, is a valid quantum operation or a quantum channel if the following three conditions hold. The first one is linearity. Okay, and this is in BH2. Okay, here I'm going to assume that it's also trace preserving. This means that this condition holds. Okay. Oftentimes, this is not required. If you want to describe the most general quantum operation, the condition here is trace non-increasing. Okay. In other words, that this is less than or equal to the trace of A. This is if you want to include like measurements and stuff like that. But for the moment, we're going to assume trace preserving. The reason being that if the operation is trace non-increasing, I can always complete it so that it becomes trace preserving, okay? And the third reason, which we have spent a lot of time understanding and using and trying to figure out exactly what it does, is complete positivity. Which simply means that the extension of this map on any state rho is bigger than 0 for all rho. So remember, the complete positivity was that if I act with the identity on any positive operator, where this operator is defined over the tensor product of my original subspace and some auxiliary space of dimension n, this is 0 for all n, for all dimensions n. And I remind you that since we are dealing with finite dimensional systems, it suffices to pick this n to be equal to the dimension of the original system. This would satisfy all the conditions, okay? But I'm giving it here in general. So if these three things hold, we call this linear map a quantum operation or a quantum channel. Now, I'm going to write a few things that I've already mentioned before here because we're going to use them. And that's the notion of a So I've introduced this isomorphism in the last lecture. I'm going to remind you again what the isomorphism is. OMB just means orthonormal basis. Sorry, one mistake. Right. We need to be careful here. This is from D2, and this is from D1. This is J, and this is I, and this is here H. No, wait, sorry. No, it was correct. I and J, and this is H2 tensor H1. Let me explain why this is. So normally, we would write the operator like this, okay? So the input space comes here, which means this J, when I flip it, okay, is the input space, is H1. And the operator returns to me something which looks like a superposition of these i's. So the input space is the bra, the output space is the ket. So this is the reason why I flipped the registers here, okay? This is very important. Also, this idea of how to understand this ket-bra notation is actually kind of useful. You can think of this ket-bra notation as an input-output relation, right? This is what annihilates whatever you input into this and creates an output, okay? Is it clear? Excellent. So if it is clear, I'm going to write here a few identities which are just going to be useful for us, and I encourage you to actually prove these in your own time, okay? The first one is that the trace is just the inner product like that. The second one I think we have already used. These are the new ones. If I put a star, I mean element-wise complex conjugation, okay? These identities are very important, and we're going to be using them a lot. Okay? Like I said, I do urge you to actually prove them. It's for ease of exposition, you may as well take H1 equals the same dimension as H2 so that they make sense. But make sure you keep the labels 1 and 2 because they are important, okay? You remember which is the input register and which is the output register.
So in identity 2, is that just a straightforward transpose, or is that the... It's
the transpose, sorry. Yes, this is the transpose. Maybe I just write a small t for transpose, so otherwise you might confuse it with my dagger, okay? Good, and with these identities, let's start. The first representation, so there are in total 4 representations, okay? The first one is by far the easiest to understand, the most intuitive one. It is also the least useful one. Aside from, let's say, looking at quantum operations on 2-level systems or 3-level systems, beyond that, this representation is completely useless, or at least very hard, very unmanageable, but I'll tell you about it because it is a very natural one to have. Indeed, it is, some people refer to it as the natural representation. I will call it the matrix representation. Let's say natural okay? There you go. So So remember, we have an input space and an output space. So what we're going to do is we're going to define an orthonormal basis at the input space and an orthonormal basis for the output space. Right? So this is my basis for the input space. This is my basis for the output space. So here we have the Fk, E of G, L. Sorry, put that there. Okay. So let me explain briefly how the logic works. Remember, this is a linear map, right? Linearity means this, which means that if I define the action of this map on a basis of this space, then I have defined it for every element in that vector space. So the idea is, okay, I define a basis for this space. Likewise, the output of this is an operator here, which I can always write with respect to a basis in the space. And therefore, what I do is I choose a basis for each one, and then I can describe the action of my channel simply by describing how it acts on that basis. In other words, how it maps elements of this basis of the input to elements in this basis of the output. Okay? Like I said, this is very intuitive, and you can see how it can be useful if the input and output spaces, for example, are two-dimensional. This is just a 4x4 matrix, but as the dimensions here increase, this matrix becomes larger and larger and larger and larger. Okay, so not very useful. Okay. Also notice that the choice of basis here is arbitrary. Okay. So if I give you the action of the map in one choice of basis, and then I ask you what is the map in another basis, then what you need to do is to realize that so let me write it cleanly here. Let me denote the matrix representation with respect to these new bases as a tilde. So let's call it U alpha K. If memory serves, this will be hold on. Yes. This is the trace of what did I do here? Alpha K. Sorry guys, I wrote this in the wrong way. So this will be Fk, and this will be the omega alpha, and V beta L, this will be the trace of GL with tau beta, okay? So it's just a change of basis, okay? That you have to do. So like I said, this is normally only very useful when your map when you have a map from qubits to qubits, simply because for qubits we have a very nice geometric interpretation. So we have a general quantum channel that takes two-dimensional density matrices to two-dimensional density matrices. In this case, you can write a very general form of the matrix representation of this map, which looks like this. This is a 4x4 matrix, okay? This takes one, hold on, sorry. I should be clear. This is with respect to the Pauli okay, so here I take maybe okay, I take the Pauli operators where I define sigma 0 to be the identity, okay? So the basis I'm choosing here, remember the input and output spaces are the same. I choose the same basis for the input and the output. And with respect to this basis, this matrix representation will look like this. right? So this is a sigma 0, sigma 1, sigma 2, sigma 3. I have a 1 here. Here I have a 0 vector. Here I have some vector m. And here I have a 3 by 3 matrix M. Okay? And this describes any quantum operation from qubits to qubits. Any one, okay? And for those of you who have done a bit more math, you will recognize that this is an affine transformation, right? Something which rotates, stretches, compresses one dimension, and shifts by a vector, okay?
And this is general.
Yes, this is a general qubit to qubit. It will always have this form, okay?
What is the reason for that?
It's just that if you write it in this basis, so remember this will be the Bloch vector, no? This, for any state, this will always be 1/2. And here you will have the Bloch vector, right? So this matrix representation tells you that how this Bloch vector transforms. So the first thing is, it has to preserve the identity, right? The second thing is that on the Bloch sphere, it could be that it moves. This vector here tells you that it moves the fixed point of the map, if there is one. And this one tells you that it rotates the Bloch sphere and stretches it, makes it into like a American football or more like a disc, or this is described by this operation here. And this is the most general thing that you can do.
But it has nothing to do with one correct.
This I'm not sure. In general, they form a group, though. So any valid quantum operation forms the group of all possible affine transformations on the Bloch sphere. So I'm sure this will be a group. I think that the only thing you have to be careful about is that because you have to maintain positivity and you have to maintain trace preservedness, this affine transformation has limits, right? I cannot shift this anywhere I want, and I cannot stretch this more than what the Bloch ball is, okay? So you have some constraints, right? Simply because you have to map positive operators to positive operators, and you have to be completely positive, okay?
And we have some kind of equivalent classes.
Equivalent classes of transformations.
Bloch spheres or something.
In what sense do you say equivalence classes?
If you have a affine transformation and you have your vector,
Mm-hmm.
move your vector and have something equivalent. Right?
No, not if it's in this way. If it's a global shift, then yes. But this is a property, exactly, this is a property of the fact that the Bloch sphere is a projective representation, right? Or not a true representation. Okay, yes. And this is all I wanted to say about this first natural representation, okay? So as you can see, it's very straightforward, okay? The second representation is by far the most useful. It's called the Kraus representation. And it's based on a theorem by Kraus concerning the general form of completely positive trace-preserving maps. Okay? So I will state and I will prove the theorem because it's one of the theorems that I promised I would prove last time. So let's do it. So the theorem is by Kraus. So let me first write the theorem, and then I'll okay, this is the theorem. Okay, so what Kraus proved is that if you give me any linear map from H1 to H2, then, and this map is completely positive if and only if there exists a set of operators, Kn, traditionally called the Kraus operators, okay, such that the action of this map on any operator in bounded H1 can be written in this form. More, yes?
In the initial premise, are you assuming that
it's completely positive?
The
yes.
map is completely, but are you also assuming it's trace non-increasing?
Yes.
Okay.
This is why this condition.
Yeah.
All right? So I'm assuming that the map is completely positive, and the theorem tells you that it's if and only if there exists a set of operators such that its action can be written like this. These operators satisfy this inequality, and this inequality becomes an equality if and only if the map, in addition to being completely positive, is also trace preserving. In other words, if it's a quantum channel, this is an equality. Okay? The proof is remarkably simple for such a powerful theorem. Okay? So let me first prove this part, and this part is actually kind of simple to prove. Okay, so let me first prove this part. So before I prove it, one direction should be trivial. So if I assume the map has this form, can everyone see why I can prove that it is completely positive? In other words, if this, then E is completely positive. Is that clear to everyone? Can everyone see it? No? Okay. So, let's assume first then. So let's assume, let me call this star, okay? So I assume that this holds, and now I have to prove that it's completely positive, right? To prove that it's completely positive, Right? I need to prove this. Right? This is the meaning of complete positivity. I give you any A on the extension, which is positive, then we need to show that this is positive. And we assume that it has this form, so if I write it out, right, what I have something like this. Right? Yes? But now notice that this operator is positive, which means that I can define any of its square roots using the polar decomposition. Without loss of generality, I'm going to pick the square root, which has the identity as the unitary. So I can write this. Agreed? Yeah? Notice that in principle, let me put it this way. In principle, this should be written by the polar decomposition as something like this. Times some u, right? And then here I would have some u dagger square root of a. Again, right? But I've chosen it to be the identity, so because this cancel out, so I'm going to write it like this. The reason why I made this point is that if I take the dagger of this, right? Now I can call this omega k, and I can call this omega k dagger, right? And this, the product of this is always positive, and the sum of positive operators is positive, so this is positive. Okay? Yes? Now let's prove the converse. Now I assume that it is completely positive and I need to prove this form. Okay? So to do that, I'm going to use a trick which will actually help me a lot because effectively I'm going to prove a second theorem along the way now. But if this is positive, let's define this is the identity which lives on this. Then you agree actually here, let's put this HN, you can put this HN if you want. Right? So you agree that that's a positive operator. Yeah? And then since by assumption E is completely positive, this implies that this by assumption, right? Completely positive means if I pick any positive operator on the extension, this must be completely positive. This must be positive, right? Let's write this out because I really want you to see this. This do you agree? This object here, if I were to write it out, it would look like that, yes? Notice that this is a basis for BH1, and this is a basis for BH1. And this, since this map is linear, what this looks like is like this, right? So it's almost like the matrix representation. Had I put here another basis for the output and taken the trace, this part here encodes the action of my channel on a basis. It's just that now I've written it with a label, right? So a way to understand this operator is you put here an element of the basis, you act with the map, and here the second register is a tag of which element in the basis you put. So you say, I put 0, here's the action of the map at 0, here's the action of the map at 1, here's the action of the map. So this state encodes, right, the action of our map. Okay? So let's call this operator, for reasons that will become clear later, by a capital J subscript E. Okay? Remember, this operator is positive. Yeah? Since it's positive and it's Hermitian, it can be diagonalized. Right? So let me diagonalize it. Oops. No, deleted the wrong thing. Okay. Yeah, let me delete this one here. I'm going to write it like this because it will signify exactly what we want to do. So let this operator is positive. I'm now diagonalizing it, okay? I'm not writing the eigenvalues because I've defined this as the unnormalized eigenvectors of this operator, okay? And since this operator, by definition, by the way, we didn't state this, but this operator lives on BH2 tensor BH1, right? Correct? Yes?
Sorry, did you say that the Kn are unnormalized?
Unnormalized, yes. In other words, yes. Is the eigenvalue, okay? So remember this, so this vector This is a vector in H2 tensor H1, correct? Yes? See? Good. And now I'm going to use this identity. This is this, right? This is important because look, if I go back here, I could have written all this as the sum over Kn tensor identity acting on I, and then on the dagger. Okay? Sorry. Right? So effectively, if I multiply this JE by some positive density matrix rho, which I put the square root of it here and the other square root of it here, and then I take the partial trace over the first register, then I get this, and since the partial trace is linear, so we had this identity, and then we said, okay, recognize that this is like this, and then we said, since the partial trace is linear, okay, we can use this third identity in conjunction with this to have the following sequence of relations. The first one is this one. Then since this operator is positive, I take its square root and I move it on the other side. This is because the trace is cyclic property of the trace. Then I write this JE in this diagonal form. Okay, to go from here to here, I use the second identity to write it like this. And then to go from here to here, I use the third identity. So here, maybe I can say from here to here is the second identity, and from here to here is the third identity. And this is the proof. Right? The only thing I haven't proved, which we still have to prove, is that this, the relationship about the sum of the Kraus operators. So to prove that, Since now we have proven that both forms are equivalent, then we have to take the trace of this. This is just the trace This next line is from the linearity of the trace, that this is Kn rho Kn dagger. The next is the cyclic property of the trace. Okay, so let's go again. Since we have proven now that this can always be written in this form, to go from here to here, I just use the linearity of the trace. To go from here to here, I just use the cyclic property of the trace. To go from here to here, I use the linearity again to insert the identity back. And then this inequality follows from the fact that this is some operator less than or equal to the identity, which means that the trace of this guy will be less than or equal to the trace of rho, and it will be equal to the trace of rho if and only if the sum of all these operators here is the identity. Okay? Okay, while you finish writing, let me just clear a bit of the board. There are quite a few remarks concerning this representation. The first and most important one is you may be wondering that the theorem doesn't say anything about the uniqueness of these operators. It just says that there exists a set, okay? And indeed there exist many sets, and the Kraus operators are not unique, okay? In fact, we can state this as a formal lemma. It goes by the name of unitary freedom of Kraus operators. Actually, I think I should change the name. Instead of unitary freedom, I think it should be called an isometric freedom of the Kraus operators. Okay? So I will state it, but I won't prove it. It's a very simple proof. You can do it at home. A quantum channel whose Kraus operators Now I'm going to define a second channel, which I called F. Okay, this set of Kraus operators F, there are S of them, and I generate them in this way. Where V is a matrix of dimension S times R. And it's an isometry, meaning that V dagger V is the identity on dimension R. Then you can show that these two channels are exactly the same. Okay? The proof is very direct. You simply just write the action of this channel on any row in this respect to these operators, then you substitute here, you use the isometry, and you show that you get back exactly the same channel but with K, okay? What is the intuition behind this? Actually, the intuition comes from here, right? Remember that this, I diagonalized it, right? But in general, any positive matrix has infinite many decompositions. I could have just as well do any unitary rotation here and define another set of operators. It's the same matrix, okay? And this would correspond to this new set of Kraus operators. Those of you who are familiar with quantum information, there's another way to understand it. This matrix here is in generally a mixed state. Right? So it's an ensemble of rank 1 things. But ensembles of rank 1 things are not unique. I can give you another ensemble, which also gives rise to the same one. These two different ensembles are equivalent. This is the statement here, but in terms of Kraus operators. Okay? So that's what it says. So the interesting question now becomes, okay, since there is no unique decomposition of Kraus operators, is there a minimal decomposition? In other words, does there exist a set for any operation E? Can I find a set of Kraus operators where this R here is the minimum number? Okay? And the answer is yes. Okay? So the minimal number of Kraus operators is equal to the rank of this matrix that we built, right? In other words, if you remember, so here it is again. In principle here, I can put as many as the dimensions of the systems. No? So if this was H2 tensor H1, this would be D2, D1, right? Or if you want the minimum, actually, between the two dimensions, right? Right? Right?
I'm not sure I get this.
So remember, this is a no, it's not the minimum. You're right. Sorry, this is H2 tensor H1 times H2 tensor H1. So this is dimension 2 times dimension 1, right? This is how many there could possibly be. But not, I remember I absorbed the eigenvalues here, right? But if the eigenvalue is 0, this won't appear. So the rank of a matrix is the number of non-zero eigenvalues of that matrix. In other words, you write it here, if I were to write here a lambda n, and I put here an r, these r equals the set of all lambda n such that lambda n is not equal to 0, okay? This is called the rank of JA. So how many, what is the minimal Kraus decomposition? Well, it's equal to what is the rank of this matrix, right? And that's it.
If you've got a non-degenerate positive operator, the eigendecomposition is usually unique up to, you know, a phase factor on the eigen. Yes,
the eigendecomposition is, but the ensemble I can always make no. So this would correspond to an ensemble. This is the ensemble that has probability with probability root lambda n, or probability lambda n, kn. I can give you another ensemble with probability pk, some fk, and this ensemble, this has 1 to r, this can have 1 to s, but okay, still gives rise to the same density matrix, right?
Yeah, that makes sense.
Right. Good. Good. But you are right. If I give you 2 decompositions of minimal rank, then this theorem again holds. The only thing that changes is that this V, instead of an isometry, now it's a unitary. Okay? That's the only thing. Good. There is another property here that is very important that I will just state, and it's very easy to prove. A map is called unital if it preserves the identity, okay? So this is the identity on H1 becomes the identity on H2, okay? If this is true, okay? And this is really, really super trivial. Just put the identity here, you know? And you've got it, okay? Why am I mentioning this? Because it's a very nice theorem as well that says, okay, first of all, let's define the dual map. If I give you a map from H1 to H2, the dual map which is normally defined via the trace. And you have the following very nice result. the original map is trace preserving if and only if the dual map is unital. Okay? Okay? Good? Okay. I promise the next two presentations are going to be quick because we've essentially proven the next one, okay? But this is perhaps the second most important way of representing maps, and you've already seen it. Okay, it's just that I haven't given it a name yet, so I will do now. It goes by the name of the Choi-Jamiolkowski representation. Okay? And it's based on a theorem which I stated last time and told you I was going to prove today. The theorem is by Choi. Notice that this map is a bounded operator on H2 tensor H1. Okay? So again, can everyone see that if I assume E to be completely positive, this is trivially true? This we've already proven, no? If this is completely positive, since this is by definition positive, and this is completely positive, this would be a positive operator. The converse is, if this is true, we have to prove that this is completely positive. But if this operator is positive, what we argued here holds. We can diagonalize it, right? We can obtain the eigenvectors, and then we can use this identity here to prove that the action of the map can be written in Kraus form, and Kraus tells us that if it can be written in this form, it's completely positive. So that's the proof. So I won't write it down because we've already proven it, okay? So a few remarks. I want to say a few things here that are basically like nuances, but it's important because if you do not know them and you read papers, you might get confused. This operator here is known as the Choi-Jamiolkowski operator. This JE written like this is known as the Choi-Jamiolkowski operator. Okay? Notice that it doesn't matter if you put the action of the channel on the first position or the second position. Everything holds, so long as you stay consistent, okay? So you pick one position and stick with it, okay? That's one thing. Now, there are, if you notice here, the way I've written it, okay? If I take the trace of this operator, this is not equal to 1. Right? Because this is not a normalized thing. Okay? So oftentimes, I will call this the physicist definition. Or rather, here, let me write it over there. So I'm only going to write this because you will often, in the early days where this kind of representation appeared, people were using it in this kind of way. So the physicist definition of the Choi-Jamiolkowski, I will put a hat on it here, just to be clear, is normally this one. Physicists normally put the same size ancilla. Remember, this is a finite dimensional Hilbert space. Complete positivity suffices if we just take the same dimension. And this state is the maximally entangled state. So here is the normalization now, 1 over d1. Okay? Yes?
My understanding is that usually, okay, in the convention we had before, the identity vector is over the space that's like the input space tends to the output space?
No.
Oh, of course, because part of the input space then gets
becomes
like the channel.
Exactly. So it's always so remember, it's the extended space.
Yeah.
Complete positivity is take the input, add an ancilla space, define an operator on this, and then this has to be positive, right?
Okay, this makes sense.
Yeah, right? Okay, what is the subtlety? The subtlety is because you have this 1 over d1. Now, when you come to these identities, you have to carry this d1 factor all the way around. So for instance, this identity that we did before, right, in our proof of Kraus, we showed that this was trace 1, or if you want h1, of this guy, no? Identity tensor, the transpose JE. This JE was without a hat. If you put the hat here, then you have to multiply this by a D1 here, okay? So more often than not, people don't use the normalized state because they don't want to carry this dimension all the way around, okay? But you need to be careful. Always check how are people defining this isomorphism. Particular, where do they put the channel and whether or not they put a normalized state here or the identity. Okay? Incidentally, since we're here, might as well tell you this now. Why do I refer to this as a maximally entangled state? Let's assume that we have qubits. Right? This is the normalized identity. There are 4 other very famous entangled states, known as the Bell states. One of them has a minus here. You will recognize that this is the normalized sigma z. This is the normalized sigma x. And finally, let me be a bit more tricky here. Let me put an I. This is that. Okay? So this operator vector correspondence tells you that essentially entangled states are like the Pauli operators. Okay? I'm only saying this because you may think that this is just an accident. A lot of the stuff in quantum info after a certain point becomes art. So if you understand this correspondence, when you look at circuits, okay, instead of actually computing all the circuits, you can use this isomorphism and these identities to move things around in the circuit and make it look simpler. Okay? Right. One final thing. Joe will kill me for this, but I have to say it. Especially if you're going to be reading modern papers, which we'll inevitably do if you decide to work with us. Is that there's another way that we can write the action of the channel, and it's through this link product. Okay? Oh, sorry. My bad, my bad. Okay. This link product has the following properties, which again I encourage you to verify. It is linear. Anything that is quantum mechanics better be linear, otherwise it won't make any sense. Which means that if you take A, there's another nice property that it is commutative. Sorry, no, not commutative. Associative. I always forget that. Doesn't matter how you bracket things, okay? It is positive. Meaning that if A and B are positive, then the link product is also positive, okay? It has the following very, very nice identity, which Joe and I couldn't see immediately, but apparently it is true. It is commutative, okay? And it is useful because you can also write the action of the channel in this way. And it's also useful because okay. So if I have two channels, I first do the first one from H1 to H2, the second one is from H2 to H3, and then I want to find the Choi-Jamiolkowski of the composite channel. This is what this means. Then all I need to do is to do the link product between the choice of the individual channels. Okay? Good. So like I said, this Choi-Jamiolkowski is very high level representation. It's very useful. The next and final representation is perhaps the one that the physicists like more. And it's the one that I think Danny started his proof with when he was deriving the master equation for you guys. And it goes by a very spurious name. It's called the Stinespring representation. Okay. And it's again a theorem. The theorem is by Stinespring, obviously. I should state chronologically, actually the way that representations happen was the reverse order that I just told you. So Stinespring came first, then Kraus, then Choi. Okay? But the original proof by Stinespring is very complicated, whereas if you know already the Choi and the Kraus representation, this proof is very trivial. Okay? So here is the proof. Let So we are going to assume that E is completely positive. So what Stinespring proved is that there exists an auxiliary Hilbert space, which I'm going to call H sub A for auxiliary. And there is a linear operator such that for any input, the action of this linear map can be written in this way. Okay? Notice that you may be more familiar with the fact that this is a unitary. In general, the original proof doesn't say anything about unitarity. Actually, this is an isometry. Okay? But I will tell you how to make it into a unitary in a bit. Let's just first do the proof. Okay. So here is the proof. So like I said, we're going to be using the fact that E is completely positive. And by Kraus, we know that there exists a set of operators from H1 to H2 such that right? This is my operator V. This is an orthonormal basis in A, okay? Right? Yeah.
Here, are we assuming that the dimension of A is the same as the number of Kraus operators?
No. Yes. It can be larger if you want.
Okay.
I haven't specified anything about the dimension of this thing, just that there is sufficient dimensions that I can do this. It could be larger, okay? That's actually an interesting question, because the next question would be, what is the minimal dimension that you can do this, okay? So, if I now compute this, and I write it out, this would look like this, sum over n prime 1 to r. I will have the trace over HA of Kn tensor n. Here I would have my rho, and here I have my Kn dagger tensor n. Now remember, rho lives in the action of this, which means that this can be written as the sum n prime. Here I have Kn rho, Kn dagger, tensor. I have to trace this system. This is an orthonormal basis, so this is delta n prime, which gives me back my operator, my E of rho, okay? And proof is really, really simple, okay? So let's finish with some remarks. I just have a few points I wanted to point out, and that will be it. So the first one has to do with, I didn't assume anything about this linear map being trace preserving, right? If it's trace preserving, then this V that we've built is an isometry. Okay? This isometry is commonly referred to as the Stinespring dilation of the linear map. Okay? So when people say Stinespring dilation, they mean this V, okay, that you construct. Okay? So you may be wondering whether or not this dilation is unique. Nothing in the theorem, no. It says there exists an auxiliary Hilbert space and an operator. And the answer is, of course, it's not unique. Okay? So, for example, and it's not unique for the same reason that, remember, to build it here, I used one particular Kraus decomposition, right? Right? This is also your question, Joe. I used one particular Kraus decomposition that had R elements. Now imagine I give you another Kraus decomposition made of F that has S elements. But this is the same map. This isometry, the second isometry will be different, but they are the same thing, no? So let me make it formal here. Then V1, this would be H1 going into H1 tensor. I'm going to call the auxiliary system now as R, at least, no? Because V1 will be the sum from n equals 1 to R. So I need at least an R-dimensional Hilbert space for this one. And I would need an S-dimensional Hilbert space for the second one, right? And obviously the two are related because I can get V2 as the identity tensor some W V1, where W just takes HR into HS. It's an isometry. Okay? Obviously, right? So we also have the issue of what is the minimal Stinespring dilation, okay? This is related to the minimal Kraus decomposition. So we have So the Hilbert space for the minimal dilation is equal to the span, and here you would have where okay. And finally, how do you turn it into a unitary, which is what most people are familiar with? So the way you do it, you say let okay? So what you do is you essentially append or introduce, pick one vector in HA, and you define a unitary operator such that when I have this state here, I get the isometry, and for the remaining space, I just complete it to make sure that this is a unitary, okay? So, since this is the isometry on H1, the above is an embedding. In fact, it's an isometric embedding. On this subspace, okay? You literally just fill in the entries to make sure that this is a unitary, and then you have it. Okay? Okay, and now let me show you how this works. For example, how we can get the Kraus operators out of this.
Sorry, one second.
Yeah.
A unitary has to be a square matrix, right?
Yes.
And do we now require that H1 and H2 have the same dimension?
Yes, I would say so, yes, yes. Okay. Or actually, yes. Or yeah, you can pad it so that it's the same dimension. Okay. Right? So let me give you the physical example. So if you go back and look at the first lecture that Danny had, he basically said, okay, look, we have a system and we have our environment, right? And the whole thing is closed, and there is a Hamiltonian here that describes the evolution of my system and my environment, right? And this Hamiltonian is the Hamiltonian of the system plus the Hamiltonian of the environment plus the Hamiltonian of the interactions, okay? And then what he did is he wrote down the Schrodinger equation that corresponds to this Hamiltonian, and then took traces, and then did all this and that and so, right? Okay, now call this the ancilla. All effectively he did is this. He basically said the evolution of rho on system S is equal to trace out the ancilla. Here I have a unitary between my system and ancilla. This unitary is acting on rho tensor some fiducial state of my environment. I might as well call it alpha. I might as well call it 0. You don't have to. You can call it plus. You can call it the thermal state. You can call it whatever you want. Okay? Doesn't matter. Here I have the dagger. Okay? It is customary in quantum info to always at least pick the state pure. The reason being that this is one way that you can simulate open system dynamics, right? I pick an ancilla system, I put it in 0, I engineer this unitary interaction, and then I throw things away. That's why I throw the ancilla away. By the way, let's do this trace. This trace is basically the sum from n equals 1 to the dimension of the system, okay? If you want. Here I put n, this is on the ancilla. U, S, A, this is on rho, tensor 0. This would be, 0. U dagger system ancilla, and here I will put an n, right? That's what the partial trace is, right? Now this acts on a different Hilbert space, so I'm going to write this as all this is the ancilla, this is the ancilla. Then I have my system rho. What does this form remind you of?
Kraus.
Those are your Krauses. Okay? So if you know the unitary interaction and you want to obtain the Krauses, this is how you do it. Okay? Just put here n, take the unitary, take the trace with 0, change the n, change the n, change the n, you get the Krauses. Okay? And that's it for this lecture. So, yes?
When you mentioned the charge of the larger Hilbert space,
This is the church of the larger Hilbert space. Yes. So this Stinespring dilation, yeah, this is a bit of a rhetoric. It always goes to the, people refer to it as the church of the larger Hilbert space. You just make the Hilbert space larger and you define everything as unitary, okay, or isometric, whatever it is. So, any more questions? Yeah.
Just in this last kind of slightly more physical example, you were mentioning that customarily in quantum info you choose the ancilla to be
pure.
But it doesn't necessarily have to be.
No.
It somehow feels instinctively to me as if you had a highly mixed ancilla, this would limit the set of operations you can do with this, but it doesn't at all.
No. Pick a mixed state, for example, pick a mixed state in the computational basis here. So what you're going to do is you're going to be taking like traces of this with other operators. You're just going to get a bunch of Kraus operators which are going to be some sort of a unitary remixing, or it's a different ensemble, right, of K. The same thing would happen. So here's what happens. If instead of 0 you pick here another pure state, you are going to get another Kraus decomposition with the same number of Kraus operators that is going to be unitarily related to the first one. Right? Because it's the same number of operators for one decomposition, the same number of operators for another decomposition. And the two are unitarily. If you decide here to pick a mixed state, meaning that the rank of the thing you put here is more than 1, then you're going to get a decomposition that has more Kraus operators than if the rank here was 1. But this means that you're just going to get another Kraus decomposition with more elements. and it's going to be the same. Okay, it would change the unitary as well. If it's going to correspond to the same map, there will be a different unitary interaction here between this and the mixed, such that you end up with the same map. But all you'll be doing is the two are going to be related by some isometry, and the isometry is the one that will bring the mixed state and interaction back into a unitary and another interaction.
So one way of looking at this is to say that mixed ancilla state is no less resourceful in terms of the channels it allows you to perform the pure one.
Yeah, because remember, it's a choice. It's not just this; it's also the operator, right? So if you fix this and you vary the ancilla and you put here a mixed state, obviously you're limiting your channels. But if you have the freedom, since you remember, if we fix this, then there are many choices of U and state here that you can put that gives us to the same thing. Okay?
Surprising.
Yeah, that's a very powerful thing. So I should mention a few tricks. So if I give you the unitary, it's easy to get the Krauses. If I give you the Krauses, how to construct explicitly the unitary operator in terms of exactly like putting the interaction with the zero is not so trivial, okay? There are tricks that you can do. There is the simple mathematical embedding that we just did now, here for example, but that does not mean that this is the easiest circuit to implement, okay? Or the easiest unitary. Because remember, at the end, you want to express this as the exponential of some Hamiltonian, and this Hamiltonian you want to be physical, so it's not, you have to do a little bit of work, okay? So that's it. There's going to be one more lecture, one final lecture, which will correspond to how do you go from the Gorini, Kossakowski, Sudarshan, Lindblad master equation all the way to the Kraus operators. Okay, and this will be the topic of the next and final lecture. Thank you very much. That's it.